All right, talking about 3.9 separation of solutions, aka the chromatography subtopic. Um, this one is a little unique, at least this video is, because I'm not just going to read to you a bunch of stuff. This is mostly reading, but I am going to point you towards a video that another educator made that's linked in the Google slides. So we'll get there in just a second. But this should be a shorter video. So chromatography, what it is, based on chromos, so like light, right? The sort of pigmentation of things. And it's really a means of separating a mixture. So if we've got a mixture of different solutions, say I poured a bunch of, pen ink, like a blue, a black, purple, and a green pen ink liquid, and I poured them all into a cup, mixed them up, I can actually separate them based upon any differences in polarity that each particular ink has. And the polarity differences can be considered as like their solubility in water, their relative solubility. So we've got three types of chromatography, paper, thin layer, and column. The one that is most important because it is, well, that sounds bad, but most important because it's most common on the AP test to see is paper chromatography because we can actually do sort of decent FRQs based on paper chromatography. So how this actually works, you have a piece of paper, right? It's paper chromatography. You draw a line near the end of that strip of paper. So, oops, sorry about that. Let's imagine this is my piece of paper. Dun, dun, dun. Dun, dun, dun. And we're drawing a line just to sort of give us a distance. Like, and then we'll put a drop of this sample, right? Our weird mixture of ink on, oh wait, no, I drew that on the wrong spot. Ink. We'll put our drop of ink right there. And then we're going to put this in a shallow layer of solvent. So we're typically going to be thinking of water. But imagine this is our little shallow, excuse me, shallow container of water. And we've got just enough water to start wetting the end of the paper, and the water will start moving up. Okay, so eventually this solvent is going to be moving up, wetting the piece of paper, and the water will travel some distance. Let's say the water travels here, right? So this is the solvent distance. Eventually, the solvent, the water, will stop traveling up the piece of paper. It might go straight to the end of the piece of paper, we don't know. As the solvent moves forward, we will see this dye also move forward, but we'll see it sort of stop along the way. So we might see the purple dye stops right here. We might see the blue dye stops right here. We might see the yellow dye stop way up here. Oh, that's kind of hard to see, but you get the idea. We've got all these different dyes in this mixture going different distances along this paper chromatography. Now, what we do to sort of analyze this is we measure the height of the leading edge of the solvent. That's this solvent distance, leading edge, and the leading edge of each dye. So yellow's sort of mark is right here. Green's mark is right here. Blue's mark is right here, and purple's mark is right here. The distance that each traveled in comparison to the solvent distance is what gives us sort of quantifiable thing, and we call that the RF, or the retention factor. RF equals the solute distance divided by the solvent distance. So in this case, the yellow dye would have a large RF, the purple dye would have a small RF, because the purple dye had a small solute distance. It only traveled maybe 1 centimeter, yellow traveled 7 centimeters, right? So 1/8 versus 7/8. Yellow would have a larger RF, and so what does that actually mean, right? I'm going to talk for a minute, and then I'm going to ask you to look at this video that's going to explain it. So when we look at the distance traveled to get those RF values, right? Here's an example with just 2 dyes. So the water traveled 8.5 centimeters, yellow traveled 5.8, and blue traveled 3.1, or cyan, right? So yellow has a higher RF value than the cyan. This means that the yellow is more similar in polarity to the solvent, right? The yellow is like traveling with the water for longer because they have more to talk about. Their polarities are more similar. Whereas the cyan is maybe more attracted to the nonpolar paper than it is to the water. Um, so it kind of depends on what we're dipping the paper in, right? I said we're dipping it in water, so let's assume that our solvent is polar. In that case, polar samples are going to travel further. If you're nonpolar, you're going to travel a shorter distance because you're not actually interacting with that water that's moving. We also call that the mobile phase. So solvent is also called the mobile phase. Oh, and this is actually at the bottom on that last bullet point. Mobile phase. Whereas the paper is the stationary phase. Okay. What do I want to say? So yeah, I want you to watch this video. It goes through an actual FRQ, and this was on the FRQ last year, so I don't think it'll show up, but probably likely to see it in a multiple choice. So in the Google Slides that are linked on Toddle, click on this slide 22. It's a 10-minute video. It's definitely worth the time. I'm just going to briefly talk about the other kinds of chromatography. So we've got thin layer chromatography. This is not on a piece of paper, but on a sheet of plastic, which is going to be really polar. And then this is a kind of chromatography we use with substances that aren't colored. So like dyes, right? Ink dyes, yeah, use paper chromatography. But sometimes we have like biological systems with amino acids. Those are not necessarily colored or visible to the naked eye chemicals. So separating them, we need something that we can see in a different way. How do we do that if they're not visible? We use UV light on the silica or alumina solvents that fluoresce under the UV light. So the thin layer is always polar, so that means your stationary phase is always polar. So if it's more attracted to the stationary phase, meaning your sample is more polar, it's not going to travel as far. It's like, I'm good staying here with this paper or this thin layer that's polar. But if it's nonpolar, relatively speaking, it's going to travel further with the mobile phase, which will be relatively speaking less polar than the thin layer. And again, we compare things by the RF values, so actual quantifying that from, how far did the solvent travel with how far did the solute travel, doing that actual math, not just the raw distances that things traveled. Okay, last thing I want to talk about is column chromatography. This is really the only thing I need. I mean, you guys can read these 2 pages, but really the only thing is column chromatography is used when you want to collect the different components of a mixture. So this is less about how far did it travel. This is more like, I want to separate this, right? I want to actually collect the dye part from the polar part from the nonpolar part, and have them come out at different rates. And as soon as I collect them, I'm going to move that test tube away. But it uses the same method of, you've got a stationary phase that's polar or nonpolar, you've got a mobile phase that you're pouring down, polar or nonpolar, and the different substances are more attracted to one or the other, and that makes them move down the column at different rates, allowing you to collect them. Yeah. Distillation, again, I'll let you read these. Pretty self-explanatory. Question 1. Most appropriate reason to perform column chromatography over paper chromatography? C. The goal is to separate and recover the parts of the mixture. That's what column chromatography is for. you're not going to see a question like this, but again, thin layer chromatography is more appropriate than paper chromatography in this case. I mean, I already read the question, but because amino acids are not visible to naked eye, they're not colored, so we'll need that UV light from thin layer chromatography. How would we set up a chromatography experiment? I mean, it's basically the same as a paper chromatography. So you've got your little piece of paper, you draw your line near the end, you drop your two samples, or I guess this is one sample, and they're all mixed together. And then you dip it in a solvent that's going to allow it to travel up, and then eventually you've got your solvent distance, and then maybe you have one of your amino acids there, one of your amino acids there. Now we're also told that serine is polar, glycine is nonpolar. In thin layer, or TLC, the thin layer is polar, right? The stationary is polar. So the polar substance, the serine, is not going to move a lot. Serine will travel less. And the glycine will travel more. Travel less. Glycine travels more. So in this example that I sketched out here, I guess this would be the glycine, and the bottom one would be the serine. Okay, so again, I do want you to watch that video. I kind of went long again. I just love talking. I do want you to watch the video that's linked in the Google Slides. Over here, slide 22 is worth it. It'll give you some prep on how to actually answer questions about paper chromatography. Awesome.